So Rins and I are from Acquaint. We are a company from the Netherlands, from the north of the Netherlands, and we are celebrating our 10th anniversary in 2 weeks from now. So we are a spin-off company from the Wetses Institute in the Netherlands. That is an academic research institute that develops innovative water technologies. And now 10 years later, we are undertaking an inline inspection at least once a week in the Netherlands. But we didn't stop at the border of the Netherlands. We started to expand into different countries in the world, like the United States, France, Belgium, and now also Norway. And our model for expanding into new territories is to work with a partner. And Shellos is our partner in Norway. And we have partners in different countries as well. Next slide, please. So this is just one slide on what we have been doing over the past few years. So in the first 6 years of our existence, we focused a lot on improving the technology, testing the technology, piloting the technology, going back to the lab. But now the past 4 years, we have delivered many commercial projects all around the world. And these are some metrics for you to have an idea what we have been doing so far. So at the bottom, you can see the spread of the diameter of the pipelines typically. And at the y-axis, you see the length in meters total. So in total, we have done 160 projects with a total length of about 540 kilometers. And as you can see, the majority of the pipelines were in the range of 300 to 700 millimeters, but we can go up bigger as well. So at the top right, a little pie chart there, that indicates the spread of the type of water pipelines that we have inspected. So it's important to understand that our technology can only be applied in pressure pipes. So that can be either a drinking water pressure pipe or a wastewater pressure pipe, also called rising main or force mains. At the little pie chart, you can see that 1/4, or a little bit less than 1/4, was drinking water or raw water, like we have done in Norway. And we have a lot of experience in pressure sewage pipelines as well. And at the left, you can see the materials we have been inspecting over the past year. In the Netherlands, we have a lot of asbestos cement in the ground, and that can be seen on that pie chart. A little bit more than half of our projects, so over 300 kilometers, have been asbestos cement pipelines. But we see a big increase, especially with us going abroad, so to other countries in metallic pipelines, like ductile iron pipelines, iron, but also steel pipelines. So at Acquaint, we are now with 40 people. We have a few field teams that execute projects on a weekly basis. We have a big data analysis team, because after the work that Hendrik just have shown in Norway, then for us the real work starts, because we receive about 80 to 100 gigabytes of ultrasound data, which need to be processed into the observations that we will share with you today. And we have a sales team, and a part of the sales team is also Rins. And Rins has started with our company a few months ago, really. And he will present the first results with you, and later on I will come back and present an online dashboard with you. This is last slide for me. So looking back at the project that Hendrik also just introduced to you, it was a ductile iron cement line pipeline, or at least, little spoiler, that was what we expected. DN 300 and a little bit more than 2 kilometers, and Rins will go through the results. Over to you, Rins.
Yes, thank you. Can you hear me clearly?
Yes. Yep.
Okay, very well. So I'm going to tell you something about the highlights of the report we've sent to the Holmestrand Kommune, with subjects on general information, the XYZ mapping, joint angles and gap widths, the wall thickness, the leaching in the asbestos cements, other anomalies, and after that, Eric will show the live demonstration of the online dashboard. So starting with some general information. On the right side, you can see the map we've sent. It's a screenshot from the report. At the top, it's the launching site. which is a small section of 20 meters of DN 250. Over to the downside at the receiving point, it's DN 300 for the remaining tracé. So the first 20 meters is ductile iron without a cement liner. Then, as Eric just spoiled a little bit, the following 700 meters is asbestos cement. Furthermore, there was cement-lined ductile iron up to the receiving point, and some cast iron spots, mainly in the bends. So the presence of the asbestos cement was unknown beforehand, which is a big result to get to know that. Following the XYZ mapping, there were some major location deviations, 7 spots we've highlighted in this map. On the right side, you see the map with the line. The green spots are where the line is exactly the same as where the GIS file said it was. And the red spots are 2 meters away from the GIS file or more. So in the next slides, I'm going to zoom in on point D and point F. Point D, as I just said, the blue line expected location is the GIS file Shellos and Holmestrand Kommune sent to us. And the measured location, the dots, are the XY points Aquaint have measured in. So the distance between this at the biggest point in this picture is 21.5 meters. Location F, same accounts for here for the lines. And the biggest deviation is 22.3 meters. This is also the biggest deviation in the whole tracé. Okay, over to some bend angles. We can also see in the data the bend angles of the corners. So here you can see the spot, and over to the right you can see a 30-degree bend. It looks like a line because it's a screenshot from the dashboard we use at Aquaint, but in reality it's just a corner. So here for example 2, same screenshot on the left side, and on the right side you can see it's a 45-degree bend. Okay, over to the joint angles and gap widths. Like Hendrik also explained a little bit, here's a picture, and here you can see a gap width of X millimeters. On the right side, you can see the vertical angular displacement of 5 degrees. So from the point you have horizontally, and then it goes down a little bit. In total, we've found 4 critical joint angles, 2 vertical ones and 2 horizontal ones. You can see them here. The numbers that are at the spots are the ID numbers of the pipe sections we've also implanted in the dashboard. So at the down left, you can see a table of the norms. So at the left side, the diameters, 250, 300, 300, the materials, ductile iron, asbestos cement, cast iron, and ductile iron. And there's always a norm for this. So at ductile iron, cast iron, it's 5 degrees. At the asbestos cement, it's 4 degrees. And our measurement accuracy is 0.25. So we build in a threshold, or a grensverdi in Norwegian, to account these as critical. So here you can see it's the same map with the numbers, and here you can see the vertical angular displacement. It's critical at 4.46 for AC, 5.71 degrees at ductile iron, 5.07 and 4.86 at the other spots, as you can see here on the right side. Okay, here we see 2 graphs. On the left side, it's the gap width in the maximum gap width in millimeters, and at the downside, it's the distance traveled in meters. So the left graph is for the asbestos cement. Here you can see both norms, and none of the points is above the norm, so no critical gap widths have been detected. The same accounts for the ductile iron and the cast iron, so no critical gap which have been detected there as well. The wall thickness. Starting with the wall thickness of the cement-lined ductile iron. On the left, you see a picture of a cement-lined ductile iron pipeline, and on the right, a schematic picture. So the wall thickness of the ductile iron is stable at around 6 to 8 millimeters. On the left side, you can see the graph. You can see the remaining wall thickness, and at the bottom, it's the distance traveled. The average is around 7 millimeters, so it goes from here 6 till above 8. Some parts are a little bit above 8 millimeters. So an interesting thing for the cement liner is there have been found two types of cement liner. The graph is the same as the ductile iron one, only it's just the first few hundred meters of the ductile iron had a cement liner of 10 millimeters. And the following section is around 6 millimeters. The thicknesses are stable for both cement liner and the ductile iron, which means it's in a good condition. Okay, over to leaching in asbestos cement. As asbestos cement pipes age, exposure to environmental factors, particularly water with a lower pH, can trigger calcium leaching within the cement matrix. You can see it on the picture on the right side. There have those are some leaching spots. It's important to mention that leaching does not remove the wall thickness. It just makes the wall weaker. On the example below, you can see on the right side, the wall thickness for this example is 28 millimeters, and the leached wall is 9 millimeters, and the healthy wall is 19 millimeters. So in this example, the leaching is on the outside, which can be through ground types or some factor of that. So the wall thickness remains the same. It's just that the leached wall is degraded wall thickness. This means that it loses its strength. So it's still there, but it's not as strong. It cannot, no forces. It cannot handle any forces. So for the leaching in this tracé, this is only the picture of the asbestos cement part. To calculate leaching, knowing the outer circumference or omkrets is necessary. Shellos did a omkrets, they measured it on the picture in the left side. In this case, the omkrets is 28.3 millimeters. So for the leaching, on the right side, you see the graph with the leached wall thickness on the average, and at the downside, it's the distance traveled in meters. So the original wall thickness is 28.3 millimeters, and the highest level of leaching was measured in the last 200 meters of the asbestos cement section. The leaching percentage reached the maximum of 50%. At the top, you can see it's more than 14 millimeters leached, which is 50% of the original wall thickness. What's interesting is that the last 200 meters, the last segment, also has the highest pressures within the tracé. So here you could see it as the graph has flipped. So it's the remaining wall thickness. And the distance traveled at the bottom. So at the end, you can see that the last 200 meters, again, the remaining wall thickness is the lowest because of the leaching. It's the remaining healthy wall thickness. Like I've explained before, the wall thickness remains the same. The healthy wall thickness is lesser because of the leached wall you can see above. So some other anomalies we found, or actually we haven't found, which are leakages. We haven't found any leakages using our hydrophone. And for corrosion, it's the same. We haven't found any corrosion in the whole tracé. A small summary of what I've just told you. Unexpected section of 705 meters of asbestos cement. the pipeline location, the XY mapping, deviates significantly from expected location up to 22.3 meters exactly. 4 critical joint angles has been found. 2 types of cement liner were observed from the ductile iron pipelines. The ductile iron and the cement liner are in a good condition, and the asbestos cement pipeline shows leaching ranging from 20 up to 50%. So now I'm gonna give it over to Eric, who will show the same results in the dashboard.
All right, thanks, Rins. I will share my screen. Do you see my screen at this point? Yeah, I see Hendrik, nothing. So that's good. Good. Okay. So thanks, Rins, for presenting the results. And what we have experienced over the past few years is that graphs and tables are really valuable, but it's always hard to put it into context. When you see the dots going up in a graph, you don't know where it exactly is over the pipeline. So that's why we have developed this online dashboard for our clients to get a better understanding of where did we find what anomalies and how can you see that in the context, like in the surroundings. So at the left of my screen, you see the different filters, if you like, to look at the data. So we're now looking at the general dashboard filter, but later on we will go to the anomalies, the joints, and the pipe segments. So here you see the pipeline that we have inspected in Norway, and this is the height profile of the pipeline. So it goes down, obviously, like often. And at the bottom, you see the different materials. So asbestos cement in this part, and then it goes over in ductile iron. Just for the people that are here that also attended the inspection, it's always nice to recognize things a little bit. So this is the point where we have where the bus was parked and where we launched the pig into the pipeline. Then we crossed the street and the pig took off. Then we went down, 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 and this is the little school where we all gathered, and this is the pit where we took out the pig again. So just for you to have a feeling how the trajectory of the pipeline was. So I'm now going to look at the anomalies. I will set the default mode. And in this anomaly view, normally we report the most important anomalies, like pieces of cement that are missing off the liner, if there is dirt observed somewhere in the pipeline. And actually the only anomaly that we have detected here were some gas pockets, which need some explanation, because while picking the pipeline, there's also a risk of introducing gas into the pipeline, which we suspect that have happened here. So at the bottom, you see the profile of the pipeline again over the 2 and a little bit kilometers. And what you can see that the instances where we have spotted gas typically are also at the higher points. So what we suspect that happened, because all the air vents were replaced or checked prior to the project. So what we believe is that during introducing the pig, we took some air with us, and we didn't give the system time to de-aerate those gas bubbles at the air vents. So this is not really a super valuable piece of information. Still, I wanted to show you this, because in sewer pipelines, for example, then accumulation of gas can cause all kind of problems like H2S attack. But for this project, it was a little bit less relevant. Still, I wanted to show you this for your information. So next step is we go to the joints view. So what I will do here on this map, so you recognize the same tracé of the pipeline, it's the same shape. Every dot on the map represents a joint in between 2 pipe segments. The view mode I've selected here is a degradation level, and a degradation level actually takes together the vertical joint, the horizontal joint, and the gap width. So if it's all higher than 0, then we give it a higher degradation level. These thresholds or these values can be set by the user. So when you look at the map here, you see a few instances where the joints got a red dot. So when I click on this joint, for example, you see that there's a vertical angle of 5.7 degrees, a small horizontal angle, but also a gap width. So it's clear that this joint doesn't sit nicely in the joint. So the pipe segments are a little bit shifted away and they're sitting under an angle in this joint. So what often also helps is when you enable the satellite view here, you see where does this joint sit, and sometimes you see a dirt road going over it with heavy traffic, for example, which is not the case in this situation. And when I go a little bit further, you see another red joint here, which has an horizontal angular displacement, but also a vertical and also a gap width, maximum 18 millimeters. So these are also the joints that Riens just showed in the PDF report, because we would like to help the client to look at the most concerning items that we have spotted. So this is a value together, but you can also extract individual measurements. So if you're interested only, for example, in the horizontal angular displacement, the color code changes from -4 to +4 degrees. And you can see that the spread of the horizontal angular displacement is colored differently here. You see more horizontal angular displacement in this curve, for example. The same you can do with, for example, the maximum gap width. But as you can see, there's a lot of information to take in, so that's why we also came up with the degradation level that takes everything into account and gives it a color code for you to know where to zoom in first. So this is looking at the joints. So when we go to the next view mode, that's the pipe segments. And basically the pipe segments, it will tell you what the quality and the dimensions are of the individual pipe segments, and mostly the wall of those pipes. So again, you see the same view over here, and I've selected the view material. So as you can see, there has been 3 materials observed: ductile iron, cast iron, and asbestos cement. This is the spread in terms of length, in terms of number of segments, excuse me. And here you can recognize the asbestos cement part at the start, and then it goes over in ductile iron. And like Riens explained, mostly the bent pieces, like here, small blue part there, those are cast iron bent pieces, which are applied almost with every bend. There's one. So that's the material. Also here, by the way, you can select the height profile, and when you zoom out or zoom in, the height profile is adapting to the piece of the pipe that is in view. Right. So as a next selection mode, I will go to the minimum remaining wall thickness. So let me explain this a little bit. So there is a mean, a minimum, and a maximum wall thickness. We make thousands of measurements per pipe segment. So a pipe segment is a length of 4 or 5 meters, and per pipe segments we make thousands of measurements on the different clock positions. To make this a little bit digestible for the user, per pipe segment, we gave it a color code. What is the minimum wall thickness that we spotted? What is the maximum wall thickness? And what is the average wall thickness? So that applies per pipe segment. And of course, as a pipeline owner, you're typically interested in the extreme. So that's why we select the minimum wall thickness. So again, per pipe segment, what is the thinnest part of the pipe that we have observed? And because we have asbestos cement and ductile iron in the same view, you get quite a big spread, and that is hard to compare. So what I open the pipe book here, I select the filter, and I focus at the asbestos cement first. So this is the asbestos cement pipeline. We have selected the minimum wall thickness, And this is a scale from 9 up to 23 millimeter. And maybe you remember from Riens that the original wall thickness was 28 millimeters. Again, let's look into the, so over here, basically the first time, just after launching the pick, the wall thickness, the minimum wall thickness. Now, let me also show you the mean one. That makes it a little bit less dramatic. So the mean wall thickness ranges from 13 to 25. But when I look to the minimum, that ranges from 9 to 23. So this is also the conclusion. The thinnest little spot of remaining healthy wall thickness of the AC is just 9 millimeters. So let's zoom into the last part of the pipeline with the smallest or the least part of healthy wall thickness. And when we take for example, one of the more blue ones, you see, and you can click on that pipe segment and then open the radar with the wall thickness. So here you see at the different clock positions in the pipeline, the wall thickness. So this is the y-axis, and the x-axis is basically the circumference of the pipeline. So here you can see that at the, 9 o'clock position, for example, there's still 11 millimeters left of healthy wall thickness. When I select this pipe segment, for example, you get another view. So this pipeline, the minimum wall thickness on basically all the clock position is heavily degraded. And you can do that for all the pipe segments that you're seeing here, but also this view tells you up till here, the minimum wall thickness is fairly stable, but here suddenly there's something changing. So sometimes it can help when you enable the satellite view to see, hey, what might be a cause coming from the ground level. And what we see in the Netherlands often, for example, agricultural activities like fertilizers or those type of activities could cause damage to the AC pipeline. And we also saw that the leaching of the pipeline is coming from the outside. Another cause could be soil type, like clay versus sand versus rocky soils, or groundwater tables. Another explanation could be that this is installed in a different time. But this is an older piece of AC pipeline, and that's just a newer part. And this is something, sometimes you can answer those questions together with the client, and sometimes it's just guessing. So that was the asbestos cement section. Let me open the pipe book again and go to the ductile iron. And let me minimize this one. So we're still looking at the minimum wall thickness. So then this is the, let me look well. So this is the ductile iron pipeline. And you see clearly two colors because in the pipe book, I selected the first layer. And the first layer is cement. The second layer is the ductile iron. And the third layer is a combination of both. So let me start with the first layer, that is a cement liner. And like Riens explained just now in the graph, we saw a big jump in wall thickness of the cement liner, which is clearly visible in this picture. You see here, the yellowish color is around the 10 millimeters, minimum wall thickness of the cement liner. And then it jumps down to around 5 millimeters. But also when I select, for example, the mean, it's all very stable. It's a very stable wall thickness of the cement liner. And you can also select the standard deviation, and that's also relatively stable. So again, like also Riens presented, the cement liner, it's an interesting observation that there seems to be a different type of pipeline, one with a thicker cement liner and one with the thinner, but the cement liner itself was in a perfect condition. So let me open the pipe book again and go to the second layer, which is the ductile iron itself, basically the most important part of the pipeline, of course. And what you see here from the start till the end, the wall thickness ranges from 5 up to 7.3, which is the color code. And this is again the minimum wall thickness. So let's go to the average one. I'm surprised that I see a jump here again because the ductile iron should be stable. See if we still have the, no, it went back to the cement. So this is the average thickness of the ductile iron, which ranges from 6 to 8. And as you can see at the start, the average is a little bit thicker. So I can imagine these are a bit newer pipelines, maybe installed not so long ago. What else can we show you? I think I'm coming to an end. So with plastic pipelines, for example, you can also select ovality of a pipeline, which is really interesting for PVC or HDPE pipelines, because those are typically causing, those are indicators that there is stress on the pipeline from the outside. Well, there's a wall thickness original, that's all everywhere the same, and diameter class, which is also, it's ranging from 250 to 300. Material and back to the integration level of the pipeline. With this, I'm coming to an end, and I think we are perfectly on time because we are still half an hour for a discussion or questions. With that, I hand it back to you, Hendrik.